customer dialed voice calls. So you have here a measure that says the proportion is longer than a particular time t, and t is the conversation time in minutes. So you see here that the conversation being longer than, let's say, 0.8 minutes over here, okay, is something like, sorry, I misstated. The probability or the percentage of conversations that are longer than 2 minutes, okay, is about 80%. Okay. The percentage of conversations that are longer than 8 minutes is about 25% or something like that. So this is an example of how the phone company measures the duration of conversation times based on a particular collection of customers and dialed voice calls. Here's now the fluctuation of the number of calls you get in a 24-hour period. Again, this comes from that telephone company. And you can see that if you are looking at the period from 8 to 9 in the morning, you get about 700 or so calls. Okay. If you look at the period over here from 4 to 5, you get about 2,000 calls in that particular period from 4 to 5. So this is the point process now that the phone company uses to try to understand the traffic demands that are coming its way and to which it has to respond. Anyway, the phone company has literally hundreds of these kinds of charts for all kinds of locations and all kinds of days of the year. You can imagine that during certain days of the year, there's more calling than during others. Here's another case. Voice call originations within 1 hour on a group of 30 lines. So there's a central office and 30 transmission lines are leaving, are entering that particular central office. And you can see again the fluctuation over a period from 10 o'clock to 11 o'clock in 1 minute intervals. Again, a point process. So this is what we call a sample function of the stochastic process that measures the number of arrivals in a particular period of time at a particular instant of time. And the instant of time is, as you see here, divided up into 1 minute intervals. So in the interval from here to here, you have this many arrivals. So this is a sample function then of a stochastic process. And of course, different times, different days, different places, you're going to get different sample functions like this. And the collection of all these sample functions across the network is the stochastic process. So one of the things you want to know is the probability distribution of these arrivals. And so you might want to know, what is the probability that in a particular point of time, let's say 10:30 in the morning, you get this many calls? Well, there is one example where you got that many, but you could have gotten this many calls, you could have gotten this many, you could have gotten this many. So there's a probability distribution of the number of calls you get at a particular point in time, in a particular location, and during a particular day of the year or day of the month or whatever. So this is the challenge now, to try to understand the stochastic process that models the statistical behavior of traffic demand. If you don't have this, there is no way you can intelligently design a network, whether it's wireless or wire-based, doesn't really matter, and provide the required amount of capacity to service the demand, and of course also to service the demand with a certain quality of service. And the quality of service also has, as part of it, the blocking probability. If you have not enough capacity, then you get into blocking, and the service quality, of course, then is reduced accordingly. Okay, now, how do we characterize all of these pictures mathematically is the next question. And organizations like the telephone companies have done this for many, many, many years. And they have developed statistical models to which the data, the actual data they have, can be matched. And so, for example, in voice traffic, the demand for service is modeled as a so-called Poisson random process. And the time duration of phone calls is modeled as an exponentially distributed process between successive arrivals. Okay. So we have here a situation where there is a point process where every time a phone call is being made, it is registered, and then the time between successive phone calls is also measured. And in the first case, we have what's called a Poisson random process. In the second case, we have an exponentially distributed time process between successive arrivals. Now, they have looked at this thing over many, many years and found out that these models work pretty well for voice communications. They don't work very well for other kinds of communications, for example, for email or for downloading massive files from a website. For example, you're downloading a movie from a particular database, from a particular website, or you're downloading graphic information from a website over the internet. So this model now really is about voice call. But in many wireless networks, for example, fourth generation 4G and 5G networks, voice is still the primary source of information transfer. So we have now the situation where we have this Poisson model, and it's been justified by the fact that a lot of the traffic demands for service and duration for between successive arrivals can be modeled according to the Poisson process. Now, the Poisson process model, you can actually derive this mathematically, comes about when you congregate, or you aggregate rather, a large number of independent events. So you have to take a situation, for example, a central office in the Washington, D.C. area. Connected to that central office are several thousand local loops going out to individual homes and offices. And so the people who pick up phones on the ends of these thousands of loops operate in an independent fashion. They don't coordinate their activity. So when I make a phone call, I don't first check to see if my neighbor is also making a phone call. Or I check to see how many people are actually making a phone call right now. I just go ahead and pick up the phone. So we have, in effect, the sum of a large number of independent demands for service with similar characteristics. Phone calls tend to have the same kind of characteristic in terms of statistical distribution of duration of the call. So that then you can show that if you add up such a large number of independent demands for service, it actually comes up with a Poisson model. And so now data sessions in other cases, for example, when you do an FTP session, or when you have arrivals in the internet backbone links, can also be shown to be modeled well by a Poisson process. Okay. But the Poisson process, as it says here, is not valid as a model for packet-level communications. And the reason is very straightforward, because in packet communications, you're transmitting typically a large file, which you cut up into pieces, and then you transmit one piece after the other, after the other, after the other. So it's a synchronous kind of communications process, whereas in voice calls, the process is random rather than synchronous. Now, the other way that you can get a Poisson process is when you combine a large number of independent traffic streams that individually arrive at random. So again, at a point of collection, at a hotspot, if you like, let's say in a Wi-Fi configuration, a lot of people are making a phone call, and this hotspot sees a lot of independent traffic streams. They may be sending data, they may be sending email, they may be sending voice communications, but the point is that you accumulate, you aggregate, again, a large number of traffic streams at one of these particular hotspots. And you can again show that this comes down to a Poisson process in the end. Now, let's take a look at some of the formulas of how a Poisson process is actually prescribed. Okay. So we have a random quantity, call it little k, okay, which is the number of service demands arriving in a particular interval of time, say in t seconds. It doesn't matter what the interval of time is. It could be hours, it could be days, it could be minutes, whatever. But t is now denominated in terms of seconds. Then the random variable k has a probability distribution. That is to say, there is a probability associated with k taking on a specific value. For example, if we take an interval of 10 seconds, then k could be the number 0, no arrivals at all in those 10 seconds, or it could be 1, or it could be 2, or it could be 29, or it could be 8,500. Whatever, k is an integer value, and it varies from 0 to potentially infinity, but of course in practice it's not infinity, it's going to be some finite number. So the random variable k then can take on these different values, these different integer values, and it does so with a probability. So the probability that the integer value is 0, that is to say that in 10 seconds, no calls arrived at all, no service demand was made, is some number. And then the probability that the number of arrivals in these 10 seconds is 1 is another value. And in general, then, the probability distribution of the number of arrivals in t seconds is given by this particular formula. So there is a parameter here called lambda. Okay. And lambda is the average number of arrivals in t seconds. Okay. So we have here a formula that the probability of getting k arrivals in those t seconds is equal to lambda t to the k over k factorial e to the minus lambda t. So if you give me lambda, if you tell me what the average arrival is per unit time, okay, then I can tell you what the probability is of getting no arrivals in that time, or 5 arrivals in t seconds, or whatever the case may be. Okay. So this average number, k, well, there is a little bit of a misprint here. There should be a period, a line above that k as it is over here. Okay. This is the average value, is given in statistical terms as lambda t, the average number of arrivals in t seconds, or lambda is the average number of arrivals in 1 second, in unit time. Okay. So if you know the average number of arrivals in unit time, that is to say you know lambda, right here, you have the entire probability distribution of the number of arrivals in t seconds. So if I know that on average, my central office of the network receives 5 calls in a second, then I can tell the probability that I get 10 calls in 5 minutes from this formula. All right, I'm just getting a phone call. Excuse me for just a moment. Okay, so here is now a picture of this arrival process here. This is where time is given, and here is an arrival. Here's another arrival, another one here. And if I take a particular interval of time, let's say from here to here, I have in that particular interval 1, 2, 3, 4, 5 arrivals in that time. And there's a probability associated with that particular picture of those 5 arrivals in that particular time. And then the time between arrivals, of course, is just this quantity tau over here. Now here's what the Poisson distribution looks like for different values of lambda t, okay? The average number of arrivals in t seconds. And it shows you that the probability of getting this many arrivals in t seconds is given by this quantity here, of getting this many arrivals in t seconds is given by this quantity, and so on. Okay, so we said that we can describe the traffic arriving at a server, okay, in terms of a point process that measures the probability of getting a certain number of arrivals within a certain period of time. And we can do this by modeling that process as a Poisson process, in which case all we really need to measure is the average number of arrivals per unit time. Let me go back to this to make sure we understand this here. So here's the formula. And if we know the quantity lambda in this formula, then for any amount of time t that we are interested in, we can compute the probability of getting k arrivals in that particular period of time t. And that gives us a complete probabilistic distribution of the service demand at that particular node, at that particular hotspot. So with this in mind, we now have a point process description of the arrival process of traffic, whether this traffic is voice traffic, whether it's mergers of files being communicated. As long as the traffic arriving at that particular collection point is independent from each other, then the collection or the aggregate of it satisfies this Poisson distribution. But now we said earlier that there is another way to look at traffic, which is the time between arrivals, successive demands. And so now we say that the probability of no arrivals in t seconds is, of course, the probability distribution, the Poisson distribution of k equals 0 in t seconds. So going back to the formula we had before, we can say if we are interested in k equals 0, no arrivals in t seconds, all we have to do is plug in for k equals 0, and we get lambda t to the 0 power, which is 1. And 0 factorial by definition is also 1. And so we get e to the minus lambda t as the probability of 0 arrivals in t seconds. So that's what this says over here, right? Probability that the time between arrivals is greater than t seconds now is the probability of getting no arrivals in t seconds. So if we say up to point t, we didn't get any, that means the probability to get the next one is going to be greater than t. And that's all we're really saying. And that probability of being greater than t is 1 minus the probability that it is going to be less than t seconds, because the two have to be complementary. It's either going to be greater than t seconds for the next arrival or less than t seconds for the next arrival. And those two numbers have to add up to 1. And so we get then the probability density function of the interstate arrival process, which looks like this. F of t then is the differential of the probability mass function, 1 minus e to the minus lambda t, or lambda e to the minus lambda t. And from that, we can compute an average value, and t bar then becomes 1 over lambda seconds. Okay. All right, so we now, with this assumption that our traffic that is arriving at a service point is Poisson distributed, if we assume that, and if we happen to know the average number of arrivals per unit time, whatever that time is, seconds, minutes, hours, if we happen to know just that number, the average number of arrivals per unit time, then we can get a complete probabilistic distribution or description of the arrival process in terms of the probability of getting a certain number of arrivals in a certain period of time, or the distribution of the inter-arrival time being exponential and an average of 1 over lambda seconds, when lambda is the number of arrivals on average per unit time. So this is now one model here for which we have a complete probabilistic description of the process. Now, of course, you have to realize that traffic is inherently random. There's no way you can predict when somebody picks up the phone to make a phone call. Whether this is a cell phone call or a landline call doesn't really matter. So the wireless network is going to have the same traffic demand problem as a wired type of network, and therefore we also need to know the traffic models if we want to design high quality wireless traffic networks. Well, here is a picture of that exponential distribution for the inter-arrival time. As you see, it goes down exponentially with time. Here is time. The larger time, the smaller the density function of the inter-arrival time. Okay. So we talked about voice calls primarily here, although I mentioned the model is applicable to other kinds of traffic. But some time ago, when wireless networks were seriously deployed for the first time, the European Telecommunications Standards Institute developed a traffic model that fits packet communications. Now you have to remember how packet communications differs from, let's say, voice traffic. In packet communications, you're trying to transmit a file, and the file is a very long one, let's say millions and millions of bytes of information. And if you were to access a channel and keep that channel for the duration it takes to transmit your entire file, you would basically hog the channel and shut out everybody else for that long period of time. So let's say, as an example, you're transmitting a gigabyte of data, okay? And you're transmitting that at a megabyte per second of capacity. So you're now looking at a duration of 1,000 seconds to transmit your gigabyte of data. And during those thousands of seconds, you are occupying that channel and you're shutting out everybody else. So in order to be fair about the use of the channel, the idea of packet communications came into the picture. And in packet communications, you have to cut up your long file into relatively small pieces, and then each piece competes for the channel with other pieces from other particular sources. And so sometimes you get lucky and the second packet right away gets onto the channel, but sometimes the second packet has to queue up behind a whole lot of other packets from other sources in order to get onto the channel. So this is a way of sharing the channel in a more equitable way, and this is basically the rationale behind packet types of traffic communications. Well, the European Telecommunications Standards Institute tried to figure out how do we model processes like that in statistical terms, and this is what we are seeing over here. So you see here there are these so-called packet calls, okay, which last a particular period of time and involve a particular number of packets. Okay. Here they are. Okay. And so then we have a number of such packet calls constitute a packet service session. Okay. And now these packets, of course, are transmitted not in synchronism, but there are random periods of time between successive packets. So the inter-packet call idle time is a statistical quantity. From here to here, there's a certain amount of idle time. From here to here, there's a certain amount of idle time, and so on and so forth. Right? And then after a packet session is over, okay, there is a timeout, an intersession idle time, until a new packet service session starts up. Okay. So we have here now a model where we have several new types of parameters. There's certainly the number of packets